Hello everyone. Today we are going to build a machine learning algorithm that is going to be able to detect brain tumors from an MRI scan. Now we are going to be using the language Python and the framework TensorFlow to build our model. Now we are going to apply transfer learning on an InceptionV3 pre-trained model. Now if you don't know what any of these terms mean, don't worry as I will cover it later on today's video. Now, if you aren't familiar with machine learning or Python very much, then this video is definitely for you as I will be going over every step in order to build this model. Okay, the first thing we need to do is to get our dataset. Now, a great resource for finding datasets for machine learning projects is called Kaggle. So once you type Kaggle onto a browser, you will be directed to a page such as this. Now from here, we are going to search up brain tumors because that's what we're trying to detect. And from here, you can click Datasets. Now we are going to choose a specific dataset over here. And if you scroll down, you will see two main folders, Testing and Training. Now the images in the training folder are used to train the model and help the model learn the data. The folders in the testing folder is used to test the model's accuracy after it has trained on the training data. Now, the images in the testing folder need to be different from the training folder because it will test the model's accuracy on unseen data. Now, notice how within these two folders, we have 4 more folders. These are our classes, and we have 3 types of tumors as well as no tumor. That is what we are going to try and classify, whether an MRI scan has a different type of tumor or just no tumor. Now, notice how we have 4 classes. And in the training set, we have around 1,400 files per class. Now, this is a small to medium-sized dataset. However, because we're using transfer learning, we don't need that many images, and so this dataset should be perfect. Now, notice how our testing folder has around 400 files, and that's perfect because you usually want an 80-20 split, where 80% of the data is training and 20% of the data is testing. Okay, so in order to download this dataset, you do need to create an account. And once you do that, you can click the download button right over here. Okay, so in order to upload our dataset to Google Colab, we do need to compress our folders. And we're going to compress the testing folder and training folder. In order to do that, just right-click the testing folder and click compress. And then we need to do the same thing with testing or training. And so you will be left with 2 zip files, testing and training. And we're going to upload these zip files and then unzip these files directly in Colab. And I'm going to show you how to do that in the next step. Now that we have a zip file created for our dataset, we need to do one last step before we upload our dataset, which is to import our dependencies, which we will use throughout the code. Now we're not going to use all of them, however. So here's some dependencies you may need to install. We're going to go with import TensorFlow as TF. And so TensorFlow is a framework we're going to be using. And every time we call TensorFlow, we can use TF. Import OS, import CV2, import image HDR, import NumPy as MP, and then from matplotlib, import pyplot, PLT, and import pandas as PD. Now don't worry if you don't know what all of these mean. TensorFlow is a crucial one as well as NumPy. However, if you don't know what all of them mean, that's okay because I'm going to cover what they mean later in this video. The cell. And now we're going to create a new cell in order to write the code in order to upload our zip file. So we're going to put from google.colab import files. And we're going to call the file that we upload train_dataset. We set this equal to the file we upload, which is files.upload parentheses. And we're going to run this. Now we're going to choose the file that we want to upload, which for me is training.zip because it's called train dataset. So we're going to upload this file. Now we need to do the same thing, but this time we need to do it for our test dataset. So we're going to put from Google Colab import files. This time we're going to call it our test dataset equal to files.upload. And this time we're going to upload our test dataset. Now, while these are running, let's write the code in order to unzip our zip files in order to actually have the dataset appear right over here under content. So we're going to write unzip training.zip. And the reason I put training.zip is because that is what my file is called. If your file is called something different, then you need to put your file name. And the same thing for my test. So unzip test.zip. So let these two cells finish running, and when they're running, run these two cells. And then once you run those cells, you should see two folders created under content. Okay, so after all my cells have finished running, if I open this folder section right here, and I go under content, you can see I clearly have a testing folder and a training folder. Now if I show the hidden output, you can see that while unzipping, it inflated all the images, and so that created the folder. Okay, so now that we've unzipped all the files, we can now build our model. And the first step to do that is ensuring that every image passed through the machine learning algorithm is the exact same shape. Now, one of the most important steps is resizing all the images so they're the exact same shape. As in deep learning, input images must have the same dimensions because neural networks require uniform input sizes. Now, we'll also normalize the pixel values by scaling them between 0 and 1. And that basically helps training performance and helps the model converge faster. So here's the code to do so. So we're going to say from TensorFlow.keras preprocessing.image import image data generator. And we're going to use image data generator to do this step. So let's run this line. Now we're going to say that train gen is equal to image data generator rescale is equal to 1./255. I'm going to do the same thing with our test. Okay, so image data generator is used to rescale the pixel values from 0 to 255 to 0 and 1 by dividing each pixel by 255. So we're dividing each pixel by 255 to ensure that the pixel values are between 0 and 1. So we can run this. Now, after that's finished running, we need to do our next step, which is train underscore generator is equal to train gen.flow from directory. And we're going to put content or /content train. And then we're going to say our target size is equal to 256 and 256. Our batch size is 65. Our class mode is categorical. And then our shuffle is equal to true. So you might be wondering, what does this all mean? So let's start for this. This basically loads our directory content train. Now from there, we're saying target size is equal to 256, 256. And that basically means that we're resizing all the images to 256 by 256 pixels. Now batch size of 65 means that 65 images are processed in each training step. Class mode categorical is required when you have multiple classes, and because we have 4 classes, we're going to use this line. And then shuffle equals true basically means that it's going to randomize the order of images, and that helps from preventing the model from overfitting. So we're going to do the same exact thing in our test generator to test gen.flow from directory parentheses. And we're going to again list our directory. We're going to say this time content /test. And we're going to pretty much just copy this exact same thing because we want it for our test as well. And then we can run this. And then we're getting invalid syntax, perhaps you forgot a comma, that's true. Comma. Invalid syntax, perhaps you got a comma, that's true. We're getting another error, we're getting no such file directory, content/train. So if we open our directory, we have training and testing. So that is true. So we actually need to rename this training. We need to name this testing. Okay, so this is great. You want to see the amount of images and the amount of classes. So I have 5,702 images belonging to 4 classes, and that's my training. And I have 1,311 images belonging to 4 classes, which is my testing, and that's perfect. Okay, so the time has come for us to build our model. Now, instead of training a neural network from scratch, we're going to use a model called InceptionV3. And it's a powerful model that has been pre-trained on a large dataset called ImageNet. Now, this model has already learned how to extract useful features from images, which we can use for our brain tumor classification task. So I'm going to copy and paste the code I have for the model. Now, I know this is a lot to take in, but I'm going to decode this step by step. So these 5 lines are pretty simple. They're our necessary imports. This is the exact line you want to use if you want to import InceptionV3, which we need to in order to actually use it in Google Cloud. Now, layers on models are key features that we use to actually build the model. And then L2 and dropout are used for overfitting, which is a common problem in machine learning. And then global average pooling 2D and dense are part of the layers in our model. So we loaded InceptionV3 with its top layers so that we can add our own custom classifier. Now it says fine-tune after 290. And so what that basically means is that it's going to freeze the first 290 layers and then it's going to train. This is very common in transfer learning. You are supposed to freeze many of the early layers and only train the later ones. Now if we go back here, we see our input shape is 256 by 256 by 3. And now, as you remember, in this step, we resized all the images to 256 by 256, and 3 is a third dimension. It's 256 by 256 by 3. Now, we froze its top layer, so include top false, so we can add our own custom classifier. Now, we added new layers, however, as well, and that's for our brain tumor detection. So let's go this step by step. So we say gap2D is equal to global average pooling 2D. And basically, global average pooling reduces the number of parameters, which prevents overfitting as well. So that is one of our layers. Then we say dense, and dense is a layer with ReLU activation, which allows the model to learn complex patterns. So we say it has 800 neurons, its activation is ReLU, which I just said, and its kernel regularizer L2 is 0.01. And this is also used for overfitting, and you want a pretty small number. If you see that your model keeps on overfitting and overfitting, then you may want to increase that number. Now we also add a dropout line right here. And so dropout again is used for overfitting, and it's going to drop a certain number of neurons. Specifically, it's going to drop 20% of the neurons, which prevents overfitting. And then we do a pretty similar thing with dense 2, but this time we use a fewer amount of neurons. We only use 300. And again, that is common in deep learning. You want to decrease the neurons as you continue to build dense layers. Now the final output has 4 neurons, 1 for each class, and uses softmax activation, which is standard for multi-class classification. Okay, so let's go through this. This is basically compiling our model, base model, gap2D, dense, dropout, dense 2, dropout 2, and then our prediction. So we can run this code now. Okay, so I know that I said that we actually compiled the model here, and that is completely incorrect. Here we just laid the structure out and made it in order. What we're going to do now is actually compile the model. I'm going to copy and paste the code again and explain each line. So here again, we import the necessary things that we need. We need to import accuracy, which we reference later in this code, as well as early stopping, which we also reference, and pickle, which we also reference. So we are going to compile the model right here. Model.compile compiles the model. Now, we use the atom optimizer, which is declared right here, because it adapts the learning rate dynamically for better performance, and it's a pretty common optimizer that you're going to use for deep learning projects. Now, our loss is categorical cross entropy, and basically, because we're dealing with multiple classes, we're going to use this. And then our metrics is accuracy. Now, accuracy is huge because you actually want to see how well the model does and whether you want to train it more or not. Now, this line, although it may look pretty complex, its function is pretty simple. Basically, if your model does the same throughout many epochs, or maybe even does worse, it's going to stop the model early. Its patience is 2. And basically, if it has the same accuracy twice or lower, it's going to stop the model. Now we see that our training parameters is step size train 85, step size test is equal to 20. Now you may be wondering what this means. So these two lines define the number of steps per epoch. So how many batches are processed in one epoch. Now how do you calculate these values? How did I get 85 and 20? So the way you do this is simple. You divide the total training samples by the batch size. So if you don't remember, our total training samples were 5712. And if we divide that by our batch size, which is written somewhere here, which is 65, you will get approximately 85. Same exact thing for test. Our test is 1311. And if you divide that by 65, you should get around 20. Okay, so now what does this mean? So here we are actually training the model. We use train generator in order to train the model. Our steps per epoch is equal to step size train, which is this. Our validation data is equal to the test generator, which we declared early on over here. Our validation steps is our step size test, which is here. And then our epochs is 7. So validation is a similar or a different name from test. Usually you may have a training, validation, and test set. Currently, we only have a training and test. However, I just named this validation. Now, what does epochs equal 7? Now, this means that it will compile this model 7 different times. And you will hopefully get a higher and higher accuracy as this model continues. Okay, so what is this line? This line saves the model, and it saves it as a pickle file. And this allows the model to be loaded without retraining, which is a very important line. So we can finally train our model by running this line. Okay, so as you can see, my model just finished training, and we achieved a training accuracy of 99.26 and a validation accuracy of 96.92. Now, your validation accuracy is your test accuracy, in other words, and it's a little more important because it tests the model's accuracy on unseen data. And so that's the percent or accuracy that you want to pay more attention to. Now, if you see our loss, it's pretty low, and that's what you want to see when training a machine or deep learning model. You don't want your loss to be high at all. So I included one more line right here, and it says scores equals model.evaluate, test generator, and steps equals step size test, print your score. So this is printing the final accuracy, and we see that it's 97. So it's close to our validation accuracy right here. In fact, it's very close. So to conclude, we achieved a loss of 0.164, which is pretty good for a machine learning model. We achieved 97% accuracy, which is, again, pretty good for a deep learning model. Now, if you enjoyed today's video, please hit that like button. And if you enjoyed our last, or if you're interested in more videos, please hit that subscribe button. Thank you and see you next time.